In this video, we are going to take a look at algebraic structures and how they relate to Haskell. So, the question that we want to ask is, can we abstract patterns in programming? And I'm not talking about software engineering patterns or design patterns. I'm talking about the patterns of the semantics of our programming. Okay, so a fair warning, if you don't like theory, this video is not for you. This video is not really practical, yet it will answer the question what the type classes Semigroup and Monoid are in Haskell. So if you're interested in that, just keep watching. But also another warning is that there will be some formal mathematics here, like set theory and function theory and stuff like that. So if you're not too familiar with that, this video might be a bit hard to understand. But I guess that the really important notions that I want to teach here will still be understandable. Okay, so let's start. What is an algebra? An algebra consists of a domain and certain operations on that domain, and then also some properties for those operations. But the really important ones are the domain and the operation, of course. Okay, so one such an algebra that we could define is the addition arithmetic. So in the addition arithmetic, we have a domain of the natural numbers, and the only operation we have is the addition. So the only thing we can do is add numbers. That's everything we can do. Well, okay. The properties that we want to have for this addition is associativity. So what do we actually do with that? Well, in this algebra, we can prove a statement like this. This equivalence holds true, and we can prove it by the properties or the axioms of this algebra. That's great. So another thing to note is that addition is a binary operation, and that is very common for the structures that we are going to look at, and also structures that relate more to computer science. Okay, so how do we formalize the addition arithmetic? Well, the domain is obviously over the natural numbers. The operation is the addition, which I'm not going to define here. I guess that everybody knows what the addition does. And the property would be this equivalence or this axiom that defines what associativity actually is. So, some more examples, like the nothing algebra. In this case, we have no operation and no property. The domain only consists of one element, which is the empty set. Now, it's not okay to have the empty set itself as a domain, because the domain has to be non-empty. But otherwise, you do not have to have any operations. So yes, this is the nothing algebra, which does nothing. The school arithmetic algebra might be a bit more interesting, where we have the real numbers as a domain, and the operations are addition, subtraction, multiplication, and division. The properties that we have are associativity and commutativity for the addition and the multiplication. So this is basically the stuff you learn at school. So something a bit more tied to real-world applications would be a perfect hash algebra. In this case, the domain is the set B that consists of all the binary strings up to the length of n. So what does that mean? Well, those are all the strings consisting of zeros and ones up to the length n. So basically byte strings. The operation in this case is some hash function h, which we don't really care for. Well, we don't really care for the definition, but the property that we want to have is that for two unequal inputs, the output should also be unequal. And that would sort of result in a perfect hash algebra. Well, now, okay, one problem here is that we have not specified that the hash function actually has to produce values of a fixed length. So in this case, one operation that we could use is simply the identity function, which of course is not really a great hash function. But hey, that's something that this algebra would allow. Okay, so something to observe here is that some algebras have things in common. So some algebras for example, as a property, have associativity for one of their functions or operations. Some of the algebras have binary operations. And that is something that, when combined, creates interesting results. So, let's define a magma. A magma is a set S with a closed binary operation. So this means that the operation takes two elements from the set S and produces a new element that is again in the set S. S, of course, would be a domain of this algebraic structure, and the operation that we just defined is the operation of this algebra. And that's about it. Well, based on this definition of a magma, we can define a semigroup. And a semigroup is an associative magma. So this means that everything that held for the magma now also holds true. But now we want to observe that this operation has to be associative. And this is where we actually have a bridge to Haskell. Because Haskell has a type class, which is called semigroup. And it consists of one operation, which is the diamond operator. And who would have guessed, the operation that you need in order to have a semigroup is exactly this operation. So, if you want to create an instance for a certain type, then the domain for your semigroup is the domain of this type, the value domain of whatever type you are using. So think of ints, for example, then all of the integers are the domain. And then the operation that you want to define that builds a semigroup on this domain, that has to be associative. The important thing is nothing stops you from making a false definition. You could define a function that is not associative, and Haskell wouldn't know that it isn't associative. But if you create an instance for a semigroup, you should do it with an operation where you have proven, or you simply are very sure, that it is associative. So, what types actually have instances for semigroup? Well, two types that we know are either and a generic list. So, let's look at the generic list. What is this diamond operator actually doing here? And if you try it out for yourself, you will see that it simply appends list. Yes, it is the plus plus. It is nothing but the list append. And that is something that we can see here. Even if you go into the source of Haskell, you will see that this is the exact definition of the semigroup for generic list. Now, we know that appending is associative. It, of course, has to be, because if you have three lists that you append in the order A, B, C, then it's irrelevant if you append B and C first and then put A in front, or if you do it simply from left to right. Okay, so another instance of semigroup is the either type. And what we do here is this operation checks if the left element has a left constructor. In this case, the other value is returned. And if that is not the case, if we have this A value, then we have to have a right constructor, and then this value is returned. So what does that do? Well, if you build a huge term of those operations with different ethers via a folding, for example, then the leftmost right constructor will be returned. So this is great if you want to find the first element for which something is true. And that, of course, is also associative. Okay, so now we can talk about a monoid. A monoid is a semigroup with an identity element. So we still have an associative operation, but now we need some element for which this operation becomes the identity operation or identity function. So the type class of a monoid needs to have a semigroup, of course. This, of course, makes sense because a monoid is built from a semigroup. So it makes sense that this type class needs to have a semigroup for this type first. And then it defines mempty, mappend, and mconcat. The minimal definition is mempty. So mempty would be the identity element. And you will see why it is called mempty in a second. Mappend is simply the operation that we have defined in the semigroup. Here you have the chance to, well, simply make a new definition for it. You could, if you wanted. For example, if your semigroup doesn't really work with your identity element, you could change it here. But that's sort of a problem. Generally, mappend and this diamond operator should have the exact same semantics. But you can change them if you want. So what does mconcat do? Well, here we have some laws for the monoid, which would be right identity, left identity, and associativity, which simply stem from the axioms that we need for a monoid. But then there is also concatenation. That is something that is unique to the Haskell monoid, where mconcat has to follow this definition. So a fold R on mappend, I was too lazy to write mappend everywhere, so I wrote just the diamond operator, with mempty should result in mconcat. Now, you might not want to use a folding everywhere for this mconcat, so you have the chance to write your own mconcat that has to be equivalent to this folding here. Okay. So let's look at the monoid for a generic list. Mempty, of course, is the empty list, because appending a list with the empty list, of course, results in that same list. And appending some list to the empty list is the same as not appending anything at all to anything. Okay, we see that mconcat is this list comprehension here, and it's up to you to figure out if this is actually equivalent to this folding that we wanted to have before. Okay, so let's look at a little problem that we have. What is the instance for a monoid for ints? What is the associative operation that we want to have for ints? Well, the important thing to note is that not every type has exactly one monoid. And the one is highlighted for a very important reason here, because some types have more than one monoid. Some have none, of course, that's possible, but some have more than one, or more than one that is sensible. And that is the case with ints. Because here we have to ask the question, what is the associative operation for numeric types? And what we will find out is that, well, the addition and the multiplication are associative. So the semigroup that we need to build for ints could be built from addition or multiplication. Well, that's a problem. Because now the question is, what do we choose? Well, in this case, we could do a little trick where we define new types for sums and products. So in this case, we have a sum with a getSum function that simply, well, returns the sum, and then we have a product. They are deriving a few classes here that I just didn't bother writing down. Okay, so how would the monoid be defined for sum and product? Well, let's look at the definition for sum. Of course, if you want to build a semigroup for a sum, then it has to be of a numeric type, otherwise it makes no sense at all. And basically, the diamond operator now is the addition. The coerce function is simply used for some type managing here, so let's not get distracted by that. Really, the definition of the diamond operator is the plus operator or the addition operator. And then there is also the function s times, which I didn't bother listing before. It is also a part of the semigroup, but you don't really need it for its definition. But here that is done. It is basically the multiplication of a sum. Okay, and then the definition for the monoid actually needs nothing but the identity element, which in this case, of course, is the sum of 0. Because, of course, adding 0 to anything, well, is the same as adding nothing. Okay, so here we see how we could work with this sum. So sum with this diamond operator actually creates, well, a sum of certain values. And here we have the exact same definition for the product, where we use the multiplication as our diamond operator. The identity element is the 1, and s times is now creating the power of a certain number. Okay, so now we know what monoids and semigroups are, but now we have to ask the question, why even define this? Why even do this? What is the point of all of this? So now we have done all of this work in order to abstract certain things within our programming, which would be that we have an identity element and that we have this associative operation. But what does that actually give us? Well, the reason, of course, is abstraction. The type classes Monoid and Semigroup are implicit promises on the semantics of our programs. What does that mean? Well, when you create a semigroup for a type, you make the implicit promise that that operation you have chosen is associative. If that is not the case, then you simply have used the type class wrong, basically. But since you have this implicit promise, that is something that another programmer might use. Because if you write a generic function that only takes semigroups or monoids, you can be implicitly sure that MMT, for example, is the identity element. But now we have to again ask the question, is this really helpful? So let's say you write a function that takes some monoids. Is it really helpful to have this information that we have associativity and an identity element? Is that actually something we can use? And the answer is yes. One use case would be a distributed computation of a huge term. Think of this term as being built by a huge folding, and we are talking about millions of elements here. Then you could, if you wanted to have a distributed system, you could write a wrapper for your distributed system that works with semigroups, for example, and then splits up this query on different servers. And since you know that this operation has to be associative, you know that the ordering of the parentheses don't really matter. So you can do it on your own. You can reorder it. And that is something very good. Well, you cannot reorder the actual elements. So for example, you cannot swap A and B. But what you could do is you could swap the parentheses around A and B to somewhere else. And this would enable you to, to maybe optimize the workflow of your distributed program, which would be great, right? Another use case is mathematical properties make mathematical proofs possible. So, since we have mathematical properties for the semantics of our program, we can create mathematical proofs that prove the semantics. So for example, a statement like this property, you could check with quick check and it will always return true. This will always be true no matter the monoid or semigroup in this case used. And that is something very good. Well, of course, you can play with the types and you have to choose a type for which a monoid is actually defined, since we use MMT here, but this will always be true. And that is something very important, which we will talk about in later videos, which is formal proving. This equivalence here is proven by the axioms of the monoid in this case. So, if we want to show that the x with the diamond operator y under the parentheses with the diamond operator MMT blah 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 is equivalent to this other term, then this has already been proven by the axioms. So doing this reordering is totally fine. And this is very important, hugely important for proving programs formally. In a formal theorem prover, for example. This is something that you can do, and that actually ensures program correctness to 100%. And The great thing is that we can use these properties that come from the definition of a monoid, for example, in order to create programs that, well, are proven. And that is a goal that we might want to have in program verification. And that is also a topic that we will talk about in later videos. Okay, so if there are any questions, please feel free to leave them in the comments below. And as always, thanks for watching. You wouldn't believe how many coffees I run through making one of these videos. If you'd like to support them, you can do so on Ko-fi, where you can, well, buy me a coffee. Any support is greatly appreciated. Thank you.